questions?
I am the next speaker, and I don't know where is my presentation. If there is anybody here that can help. Yeah, you're right. Thank you. So, nobody here to present me. My name is Ricardo Valls. I am the president of Valls Consultant, and been working in geology for 35 years. And many of those years I have worked into trying to develop a new way to approach the mining exploration. And I would like to start today with a short story, the story of three hungry geologists. I think you can relate that. These are three geologists, very hungry. They came to a new place, and somebody told them that there is a place called kitchen, and in that place there is a big bowl of soup. They're hungry. So they see some dirty dishes, they walk on top of some crumbs, they have some smells. Okay, there should be something there. So these three guys get to the kitchen. Of course, it's all dark. One of these geologists, the oldest one, decides to do this systematically. So he goes to the end and start walking systematically. And he said, I'm gonna walk until I find this bowl of soup. The second one, younger one, believes that he can win the Powerball too. And he said, okay, I'm just going to, walk around. Maybe I will stump into the bowl of soup. The third one went to the wall and just turned on the lights. This presentation is about this third geologist, the one that's turned on the lights. And I should add that to the title, because this is, what I'm going to explain you today, is the most effective way to find a deposit. I cannot put it there, but if it is there, no matter where, I'll find it. So why we need this thing? A normal exploration will start, with doing some research, then you will have some satellite imagery, you will do some mapping, you will do some geochemical sampling, geophysical sampling, and at the end, you probably will you interpret the data, you find a target, and you start drilling. This takes a lot of time and a lot of money. There are, of course, companies that try, like the young guy walking aimlessly with the hope to find the bowl of soup, try to grab the cat by the tail, and usually that's the result, because Mother Nature doesn't believe in luck. I'm going to tell you a real case story from Colombia. This happened 3 years ago. It's Company A. They did the whole thing. They did the mapping, they did the chemical sampling, they did the physics, and they get the targets, they did the drilling program, and they found a mineralized zone. Great. Another company came and bought the license next to them. And they say, well, we know where the mineralization is. Let's start drilling. I'm not joking. They didn't do anything, no drilling, no nothing. They just, the first day, they put 5 machines and they start drilling. And of course, 0. So what happened in reality? There was a fault right in the middle of these 2 targets. And of course, that thing moved to the north. Real case story, I was there. So, how does this work? By the way, I didn't mention, this is based on lineament analysis. Lineament or structural analysis, you want to say. So we start by selecting the area, doing a 3-dimensional modeling, row diagram, data processing, and then the graphical results. So for the selection of the area, let's say you have that area over there. The most important thing that you need to know is that you need to process an area that is larger than your target area, because there is always deformation happening at the borders of your target. Also, the area should be big enough. So, for example, if you have a circular structure and you have a very small area, that circular structure could look like a linear. So you lose the structure. So this thing works for area of 25 square kilometers minimum and up. So I'm going to show you some of this lineament analysis. This is where we define my secondary in blue, that is tertiary, and circulars up there. A normal lineament analysis, and this is done by hand. No computer can do this. They can help, but this is done by us. A normal lineament analysis may provide you with 250,000 tertiary lineaments. So it's a big work. So let's see a practical example. Let's say, and I usually do this live, so people will do it, because it actually takes a couple of minutes. Let's say that you have this map, and we're going to draw some lineaments there. So we start with main lineaments. You can see. This is also called in geology creekology. You just follow the creeks. The creeks are a very good representation of the structure. If you have a river that goes here and turns left, that's a fault, for sure, unless there is a dam. So this is an example of some main lineaments. These are secondary lineaments. The difference between a main lineament and a secondary lineament is just the size. We call main lineaments lineaments that are bigger than 10 kilometers. One thing to know is that there is a lot of structural publication that shows that the main lineaments are active always. They never stop being active. And that is why we have been able to do this kind of analysis in places, for example, in Nevada, that are covered by sands. We are able to figure out where are these main lineaments. So, circulars, a couple of examples there. And I didn't put the tertiary because it would be too many. But the next step would be to put them all together. And the reason why we put different colors is not because it's for pretty or nothing like that. It's because we have a program that allows us to count or to interpret the amount of lineament and the type of lineament with different colors. Okay, that's why there are different colors, but you can put it all in black and white. The next thing is to find out how many intersections you have. They are not all there. There are just a few examples. So you have intersection between main and secondary, main and tertiary, main and circular, secondary and tertiary, la 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 la. So, how do you count it? And we right now have a program that does all this for us, but it can be done manually. We did it for many long years. So we start by putting a grid, and the grid will be defined by the degree of detail that your work requires. Let's say this was a 500 by 500 meters, so it's a 1 to 50,000 scale. And then we count how many structures and how many intersections of these structures are on every single square. Okay, so that's the whole thing. Another example there, we have, for example, one main, one circular, 2 intersections between main and circular, and 2 total amount of intersections. So with all that, we create a table, which I will show you a little bit later. But now I want to talk a little bit about the plastic part, because this is really very interesting. We do lineament, that is just using or a digital elevation model, or a topographic map, or even a map obtained by a drone. It's just lineament. But we can also model 2 types of tectonic events, strain and stress. For the strain, or the plastic deformation, we create a model. Mud, sand, in a box, we mark the main structures, and then we subject this model to different types of deformations. Every time you deform, you apply a pressure or a tension, there will be a group of lineaments that will open, and there will be a group of lineaments that will close. Of course, you want to know the location of those that open, because what you're looking for is that bowl of soup in the kitchen. You need the space. You may have the most beautiful biochemical anomaly in the world, and that could be just a nugget on the surface. What you need is a space. So my main objective here is to tell you that going from here to the future, the main idea for exploration is to try to find where in your target is the space that could be filled or not by mineralization. So every time we do a deformation, we take a picture, we redo the model, we do the same experiment 3 times, and there is a total of 36 types of deformation that we can do. And every time, as I said, we get some folds that will open and some folds that will close. And this is how it looks afterwards. We put all these pictures together. In red are those places that no matter from where the pressure came, they remain open. These are our main targets for plastic deformation. Of course, if you know biology, by looking at the geology, that in this area there was just a compression, it was clear, I mean metamorphosis shows you that, then you don't need to do all the model, you just do the one that corresponds to your area, and that makes the process shorter. And that looks like this in a map. Okay, so of course these are the targets. This is plastic deformation. Now, we also have elastic deformation. And for elastic deformation, the elastic, we use gelatin. Make a model of jello, we mark the lineaments, we put a polarized paper below it, and then we put a light and do the same deformations. Everybody remembers the microscope with the nickels. This is the same thing. Wherever you get the red thing, that is places that are opening. In blue are places that are closed. The thing is that with yellow we have 2 advantages. Once you eliminate the pressure or the deformation, it can come back to the original size, so you don't need to redo the model, it's much faster. And the other one is at the end you can eat the gel. Again, that's the graphic representation, and then you combine both of them. And if you ever have this situation, that you have a combination of plastic and elastic deformation in the same place, and all this happen before you put a foot in the ground, you know exactly where is the potential bowl of soup. So that allows you to reduce the area of exploration the first day. And as usually we reduce the area by 50%, that's the minimum, sometimes up to 75%. We concentrate directly in those places where the potential is. So, now you can add other sources of information that you have from the region. You have geophysics, geochemistry, mapping. You can add all this to this lineament process. You select the areas and you add it. Now, one thing that is very important to know, to add a type of information, the information should cover the whole area. If it is only a part, it doesn't work. You need to have, if you're going to use geochemistry, it should have the geochemistry for the whole region, not for some little piece of your exploration area. So, how the integration happens? Very simple. Well, very simple. We have a way to convert all this data into digital data. Sometimes we just buy the information from a provider, and that is digital data already. And I'm not sure if I have it here or not, but if I have it, I will show you how you can convert a map, a physical map, into digital data using Adobe Photoshop. It's a very simple way. And you put all this together using correlation analysis. And the difference between our method and the hyperspectral method is that the hyperspectral method, the one that uses satellites, they have, like, for example, 500 layers. But if they want to interpret that, they need to take layer 3, layer 93, and layer 6, put it together, and that is argonite. And then they need to take layer 2, layer 25, and whatever, that is silica. With our method, we get all these layers compressed into one layer, which we call the prospective map. Now, rose diagrams. This is another thing that geologists used to do in the field. So you just do your measurements on a grid, it doesn't need to be an actual grid, but you get the information. And here, by the way, if somebody wants this presentation, please contact me later. I will send it to you, so you don't need to write down nothing and just listen. So I have this flow chart developed that allows you to convert a rose diagram into a number or a figure. Okay, you just follow the yes, no, yes, no, yes, no, and you get an information. That's how you get the rose diagram also as a digital data. So this is how it looks, the process, okay? You have a table of Excel that comes from here to the next room. And it has many columns. First, all the main, secondary, tertiary, all the intersection, main with secondary, all the geophysical, all the geochemical, all the geological. I mean, some of these tables are really a meter and a half width. And you do some normal processing with them, determining the distribution law to eliminate the logarithmic effect, the normal stuff. Now, the most important part is the correlation analysis. The correlation analysis allows us to get these pictures. And I'm going to try very quickly to explain how this works. You have all your correlation and you put it from the +1 to the -1. And you get the first positive correlation. Let's say element A and B. So you put element A, 4 centimeters, 5 centimeters, element B. And you get the next element that has correlation with these two. Let's say element C. And element C is 0.98 with A and 0.97 with B. We convert those correlations into distance. The smaller the correlation, the longer the distance. And then you just make an arc from A and from B, and when those two arcs intersect, that is the location of point C. So that is how you get these graphics that are extremely informative. You can rotate it if you start doing the graphic from another pair. And at the end, you get a coefficient, which I call the range correlation coefficient. That coefficient will map your targets without going. This is before you get into the field. We are able to, if you have in your area, you have a known mineralization, you can estimate this RCC for the type of mineralization that you're looking for. We have done this experiment, for example, for Inco or Valley, where we had a coefficient for the copper deposit different for the coefficient for the platinum deposit. So you can really make this as detailed as you want. Factor analysis also works very well. The problem with factor analysis is that you really need to know what the combination of M, and C means. It requires a little bit more of geology that sometimes at the beginning we don't have that kind of knowledge. So the results, as I said, instead of having 50 different maps, you have one map, which we call prospective map, that integrates all these things and just gives you targets. As I said, we usually are able to reduce the area of exploration by minimum 50%. And that means that if you have a budget, you had a budget of $1 million to explore 100 kilometers, now you have the same budget to explore 50 square kilometers. Imagine how much efficient you can be. These are some graphical representations. I just want to show you how the road diagram maps works. This is again a true case story, again from Colombia, from, I cannot mention the company, but all their mines, the known mines, were here. And we have shown them that there is the same potential down here, and they are exploring at this moment. So that's it. I just tried to, I tried to get into my 25 minutes. If you have any questions, please. Yes?
Yeah, my question is, when you have all the variables and you have all of when you rank correlation on all of them, and you said you rank them by correlation.
Mm-hmm.
And then the next step is you add distances.
Okay, I just make a coefficient called the coefficient L in remembrance of my wife, Ludmila. Is L equal 4, and what 4, because I have done this many times, at 4 centimeters, if you start with a distance 4 centimeters, it will fit in a page, believe me. Okay, so you start, you say L equal 4 plus, parenthesis, 1 minus the correlation minus divided by the maximum correlation. Okay, so when the correlation is 1, you get 4 centimeters. If the correlation is 0.98, you get 1 point something. So you convert all your correlations into distance, and then you start putting these two, you start with the 2 first, and with the semi-arc, you define the third one. You can do that if you want the graphic. The graphic is very beautiful, and it's
But adding the distance, that you're normalizing the data. Is that what?
No. You just convert correlation, the value of the correlation, into a distance. No normalization. It's just that you will start. The maximum correlation you have will be at 4 centimeters away. The minimum correlation that you will have will be, 7, 8 centimeters away. And if you have a negative correlation, you put dots. If you have positive correlation, you put a straight line, just for this. But this can be done even simpler. Start from the bottom. Okay, let's say you have at the bottom of the correlation, you have a negative correlation between silica and chrome. Okay, so if they are if this is a negative correlation, you put silica in the numerator and chrome in the denominator. Okay, you start with that. Then the next pair is silica and iron, also negative. So you keep silica there, you put iron at the bottom, and you start combining these elements, and you will get your correlation. What happens if you have more, and you always will have more than one process, because unless you don't have mineralization. If you don't have mineralization, then you're only going to have one beautiful correlation that uses all the elements, because there are no difference between a mineralized zone and the regional thing. So you should have a problem when you're going to try to put, for example, the chrome on the denominator, because it is in a positive correlation with this element, but at the same time, before, you said that the chrome cannot be here because it must be here. So that means that chrome, you take it out and you start a different coefficient. And that way you get 2, sometimes 3 coefficients. One of those 3 will be the type of mineralization you're looking for. The other one will be just the regional geology. Any other question?
You're creating confounding variables. So you're creating more variables to look for confounding.
At the end, I only work with one RCC, one range correlation coefficient, for the type of mineralization that I'm looking. And that RCC may be a huge coefficient. That's why we can put everything into just one layer. We don't do combinations. We just do one map, drill here. Or actually, not drill here. Go and explore here. I just turn on the light in the kitchen and I show you where the bowl is. Now you need to go and find if the bowl has soup or water or whatever. That is when you apply your chemistry, your physics, etc. But at least you're going to concentrate immediately where the potential is. I'm going to be here tomorrow too. If you find me out there, you want to ask questions, please do. Thank you for your attention.